Week 3, correct? And so week 4 we have our test. What I'll do is I'll post an old exam from the past, except it might not, correlate one for one for this class because I cover things slightly different last time I taught this. But you can use that as just to get an idea of the length of the test.
Is some sort of study guide?
I'm sorry?
Is some sort of study guide?
A study guide?
Yeah.
Sort of, yeah. It's not a comprehensive study guide, but you can use it as a study guide. It's not guaranteed that all the concepts are going to be on there, that kind of thing.
And we can use that as some kind of practice test.
Yeah, you can use it as a practice test. That's always good. The tests will be similar. I mean, they're going to be similar style questions for sure, but a little different too. All right. There are no questions. We'll just continue with Chapter 3. Chapter 3, we were looking at the composition. If we want the composition, then the most common way of expressing the composition is not by percentages. For example, if we look at water, water is 11% by mass hydrogen and like 89% by mass oxygen. Or by atom, it's 67% hydrogen, 33% oxygen by atom. But we don't usually, we just write the formula. So it's 2 atoms of hydrogen, 1 atom of oxygen, or 2 moles of hydrogen atoms, and 1 mole of oxygen atom. And so what we want to do is we want to determine formulas. So how do we determine the formulas? And so the best is we want to determine the molecular formula. But not everything forms molecules. For example, some things just form atoms, like helium. This would just be the formula of helium. What about something like sodium chloride? Does sodium chloride form molecules?
It's ionic.
No, it's ionic. It doesn't form molecules. And so we can't call it a molecular formula. Molecular formula would be incorrect for sodium chloride. Instead, what should we call it instead of a molecular formula?
Empirical.
It would be an empirical formula. But you usually call it a formula unit because all of 3 of these are empirical formulas. And so it really doesn't differentiate if we just call it empirical formula. But you know what? All of these are also formula units. But, the formula unit for water is the same as the molecular formula. But the formula unit for an ionic compound is going to be the empirical formula. And so the empirical formula, we know. Empirical formula would just have the simplest whole number ratio, 1 to 1. The interesting thing, a formula unit can be for all 3 of these as well. All right, so how do we determine these things? The way we determine formulas is by chemical analysis. Chemical analysis is a very broad branch. So for example, when we're doing our titration, we're analyzing, that's chemical analysis. We're analyzing those solutions or whatever. But in this type of chemical analysis, we're going to be looking at elemental analysis. What elements is a compound or whatever we're looking at comprised of. Elemental analysis. And in elemental analysis, there are many techniques. If we look at the techniques can you name some? Maybe these aren't so. XPS, Have you heard of XPS? XPS is X-ray photoelectron spectroscopy. So you just bombard the sample with X-rays, and then what happens is it ejects electrons. You know, X-rays can knock electrons off. X-rays are what we call ionizing radiation. That's comprised of high energy light. It can knock electrons off, and then, you know, as electrons rearrange, it emits light, and those light patterns we can use to identify elements in XPS.
How's that different from XPF?
Not really. I mean, X-ray photoelectron fluorescence, or XF. A lot of these are very similar. You know, just different acronyms for different things. Like, you don't have to know how it works. Just there are many techniques, etc. One of these is combustion analysis. Combustion analysis only works if it burns. Not everything burns. Typically, when you think about what burns, does sodium chloride burn? No. I mean, have you ever tried to burn sodium chloride? Well, I shouldn't say no, because at a certain extreme, under certain extreme conditions, you could get the chloride in sodium chloride to burn. Does helium burn? No. Water? No. Typically, what types of things burn, combust? Hydrocarbons. Not just hydrocarbons, alcohol, you know, like if you have alcohol, it's pretty flammable. You know, acetone, nail polish remover, that kind of stuff. Nail polish remover is what we call a ketone. And so combustion analysis, all those types of compounds are called organic compounds. Although not all organics burn. So combustion analysis of organics. And so you wouldn't analyze, let's say, something like sodium chloride or other salts using combustion analysis. It just wouldn't work. You'd have to use some other technique. This is why we have lots of different techniques for this. For XPS, AA, these types of things, what we do is we get either the mass of each element. Okay, so one, it's either the sample mass plus mass of each element, or, you know, these are the results. The results, or two, the percent by mass composition. So let's say you send out a sample, the sample comes out 11% hydrogen, 89% oxygen. Well, that's water. That kind of sound.
Does AA stand for atomic absorption?
Yes.
Okay, just making sure.
AA or AAS. Atomic absorption, I told you about, you know, I was flipping channels, and did I tell you about that? The flame test. Well, if you put a detector, you can tell how much, you know, depending on the intensity of the color and the flame, you can tell how much was in there. So it's very quantitative in that matter. Plus, it's also very qualitative as well. And so we got the percent by mass composition. Whereas in combustion analysis, we get a little different, you know, results from that. The results are typically it depends on what the organic is, but typically, one, if it's a hydrocarbon just is a compound of hydrogen and carbon, or a hydrogen, carbon, oxygen compound, we're going to get CO2, grams of CO2, and grams of H2O. And then from the products of the combustion, we can figure out what's present. Or two, we'll get this plus other stuff, if there are other elements present. Okay. And then from that, we can figure out the formula. So once we get these results, then what we do is we take those results and then determine the formula. But the formula we determine is not just any formula. We determine the empirical formula from this chemical analysis. And then if it forms molecules, again, not everything forms molecules. But if we can determine this, either the molecular mass or the formula mass, molecular or formula mass, formula mass used in the context of this. This is just for molecules. You know, if we have a salt, salts are usually written as empirical formula. It's the formula unit. For molecules, what we want is we want the molecular formula mass or molar mass in order to get the molecular formula. And so we try to do an extra step if it forms molecules. We want the molecular formula, not the empirical formula. And so for something like hydrogen peroxide is empirical formula HO, but the molecular formula H2O2. So we just need to know how much a molecule weighs. If we know how much a molecule weighs, then we can compare it to the weight of the empirical unit. If the empirical unit and the molecular unit have matching weights, matching masses, then they're the same. But if there's a mismatch, then the molecular formula is not the same. And so let's do this. You guys are familiar with going from percent? Okay, so examples of this, it would be going from percent comp to grams, then from grams to moles, and then the formula is the mole ratio. And so from here we get the simplest whole number ratio, and that's our And so let's take a look at a specific example of this from the homework. Go to chapter 3. Pull this up. So normally what I do is I just read through all the problems and look. All right, so number 88. By analysis, a compound was found to contain 26.58% potassium and 35.45% chromium by mass. So this is number 88. So 26.58% potassium and 35.45% chromium. The remainder was oxygen. And so how much oxygen do we have? Well, basically it has to add up to what percentage? It has to add up to 100%. So all I'm going to do is I'm going to take 100 minus this minus that. And that's going to give me the percent oxygen. And so 100% minus 26.58% minus 35.45% is equal to, let's see, so 100 minus 26.58 minus 35.45. And that gives me 3.797. 37.97% oxygen. Okay, do you guys recall what we do next? We assume a 100-gram sample, and then what? We go to grams here. And so that's very simple. So this is going to go to 26.58 grams of potassium. This will go to 35.45 grams of chromium. And this will go to 37.97 grams of oxygen. And then formula is not a gram ratio or mass ratio. A formula is a mole ratio. And so we need to convert all these into moles. Let's go ahead and do that. And so I don't have the molar mass of potassium memorized. And so we'll just look it up on the periodic table. Here it is 39.10. I only go 2 decimal places, and I'm going to round it. I know I've talked about rounding off error, but it'll make your life a lot easier if we just go ahead and do that. Typically, we just need 4 sig figs in everything. So that's what we shoot for here. So I'll get 26.58 divided by 39.1. 0.6798. 0.6798 moles of potassium. And then chromium is molar mass is 52.00. So 1 mole of chromium, and I'm rounding this, 52.00 grams. 35.45 divided by 52. 0.6817. Okay, I'll go 4. I might carry the 3 here. This was 1 extra digit. There are reasons I try to carry as many digits as possible because when you are a little bit overzealous with rounding, it's hard to get whole number ratios sometimes. Oxygen I have memorized. Do you have it memorized?
16.00.
Yeah, 16.00. The O's are important because we want 4 sig figs. And so this is 37.97 divided by 16. 2.3731 moles of oxygen. Okay, so we set up the mole ratio like this. So it's going to be K 0.6798, CR 0.68173, O 2.3731. Does that look like a good formula to you? No. This would be a violation of the law of multiple proportions, right? Because this would indicate that, you know, atoms are infinitely divisible, or not atoms, elements are infinitely divisible. Otherwise, there's no such thing as an atom. So what do we do?
Divide by the smallest.
Yeah, we'll divide by the smallest. So the smallest is this one here. So we'll go 0.6798. This is going to be divided by 0.6798 and divided by 0.6798. And so the potassium to 4 sig figs will be 1.000. The chromium will be, 0.67173 divided by 0.6798. Chromium comes out to 1.0028. Oxygen, 2.373. 1 divided by 0.6798. 3.49. 3.4909. So what should we do in this case?
Multiply by 2.
Yeah. We probably should multiply by 2. Does that make sense? I feel uncomfortable rounding this. What would you round that to?
Round it down.
You'd round it down. So, you know, maybe it is KCR03. But No, this is too much to round. And so we'll multiply by 2. Sometimes you'll multiply by 2, sometimes you'll multiply by 3, sometimes you'll multiply by whatever. And in the book they suggest, you multiply by 2, it still doesn't look right, and multiply it again. And multiply it again until it looks right. And so they give an example in the book where they multiply by 8, but it's hard to see if you multiply by 8, unless you do it in sequence. But in this case, I think multiplying by 2 is going to work quite nicely. This is going to be K2, CR. This is going to be 2.0036. This is going to be this is still my calculator, 6.9818. All right, now we have a choice. We could multiply it again, or we could try to round it. Would you feel comfortable rounding 2.0036 to 2? Yeah, I'd feel pretty comfortable rounding that. What about this one? Would you feel comfortable rounding this to what? 7? Yeah, I mean, this is pretty close.
Possibility.
If we round this to 1 sig fig, yes, 7. If we round it to 2 sig figs, it'd be 7. So I don't think there's any problem with rounding this one. And so we end up with K2CR2O7. Wow, do you guys remember nomenclature? Give me the name of this.
Potassium chromate, dichromate.
Potassium dichromate. Good. Dichromate. Potassium dichromate. So this chapter deals with nomenclature also. Do you remember the names of the ions? You have those memorized? Do you have flashcards, or how did you guys memorize the names? Flashcards. You still have those? It'd be good to go back through those. It's like everything else. If you don't see it, if you see it every day, if you see dichromate every day, until the end of the semester, I don't think you'll forget. But what are some ions that you should use flashcards for? Well, I'm going to take a slight tangent here and talk about the ions that you should know. What are the ions that you should know that end in 8? Like this one ends in 8, dichromate. Right? A lot of these you have to just memorize, and so tell me all the 8s that you just need to memorize. Well, nitrate, there's a trick for nitrate that we don't necessarily have to do. Well, one is oxalate. Oxalate is just straight, you got to just memorize that. What is the formula for oxalate ion? C2O4 and the charge? 2 minus. So that's the oxalate ion. Acetate is another one that you just can't avoid it, you just have to memorize it. What is the formula for acetate ion? C2H3O2 minus. These are the memorized ones. Maybe you still have all these memorized. What else? Permanganate. Permanganate formula?
MnO4.
Good. MnO4 minus. Permanganate. What else? Chromate. Good. Chromate is
CrO4.
CrO4.
2 minus.
2 minus.
The
Dichromate. Cr2O7 charge. What else?
Bicarbonate.
Bicarbonate you could derive. Yeah, we want to try to keep the memorization to a minimum, and therefore if we could derive it, we don't have to make a flashcard for it necessarily. I don't use flashcards because I need to get it into my muscle memory, the act of writing it down. And so the way I memorize these is I just wrote it. Like acetate, I remember writing it. I think I wrote it like, I can't remember exactly, but I think in order to memorize it, I had to write it like 300 times or something like that. And then after that, it's automatic. Acetate.
It's like a punishment to write up on the board, 300 times.
Yeah, right. There's others that end in 8 that we should have memorized. Well, phosphate we can derive. What others should we have? Cyanate is one of them, but let me see. Some common polyatomic ions. Acetate, carbonate we can derive. Hypochlorite we can derive. Chlorite we can derive. Chlorate we can derive. Perchlorate we can derive. Chromate we can't. Dichromate. Cyanide is a different one. Hydroxide, nitrite, nitrate we can derive. Oxalate, permanganate, phosphate, sulfite. Thiosulfate. I think that's it. There's cyanate, but that's not so common, and thiocyanate, that's not so common either. So these ones we memorize. There are 2 more that we memorize off the periodic table. One is borate. Do you know what borate is? Yeah, good. BO3, 3 minus. We memorize that one. And silicate. We memorize silicate. What is silicate?
SiO4. 2 minus.
SiO4,
4
4 minus. So I memorized that. And the rest, there is a pattern that we can see, to help us minimize the amount of memorization we do. A pattern goes like this. If you know borate, then carbonate's easy. What is carbonate? CO3.
2.
And then nitrate's easy. What is nitrate? NO3 minus. And then after nitrate is oxygen, but there's no oxate. And then there would be fluorate. What would fluorate be? FO3 minus. This would be fluorate, but fluorate has some problems. And but we'll talk about the potential problems fluorate might have in a minute, because fluorine's special. Everybody has to treat fluorine special. What is special about fluorine? Fluorine always gets its own way, Yeah, it's so reactive because it has such a high, electronegativity and whatnot. But chlorate's okay. What is chlorate? ClO3 minus. And then bromate, BrO3 minus. And then iodate, 3 minus. So these are all the 8s. Carbonate, nitrate, fluorate, chlorate, bromate, iodate, etc. If we know silicate, then we know phosphate. What is phosphate? PO4, 3 minus. And then sulfate? Actually, I should go with a different color here. PO4, 3 minus. And then sulfate? SO4, 2 minus. And then, selenate?
SeO4 2 minus.
Tellurate?
TeO4 2 minus.
TeO4 2 minus. Arsenate?
ASO4 minus.
ASO4 3 minus. That's probably enough. Do you see a pattern? Yeah, well, look for a pattern, and then that helps you remember it. That way you don't have to memorize it. So something like bicarbonate, I know bi. Bi means what? Well, no, bi and anions. Di usually, di versus bi. Normally when we have something like bicarbonate, it doesn't mean we have 2 carbonates. Dichromate, D. If this were bichromate, I treat it differently. Di means usually 2. But if we have 2 chromates, what happened to the oxygen? Well, one of the oxygens had to leave. That's what happened. Because oxygen doesn't like to bond to oxygen. And so one of the oxygens left. But when we have bi, it indicates something else.
Wait, oxygen doesn't like to bond to oxygen? But even though there's tons of O2 in here?
There's tons of O2. Oxygen doesn't like to bond to oxygen with a single bond. You'd have to have a bridging, what we call, we'd have to have this kind of link. This kind of link happens. And so when we have oxygen bonded to oxygen with single bonds, like this, we call it a peroxide bond. One of the characteristics of a peroxide bond is they're unstable. And so this is why they don't like to bond. This could bond, but it would be a peroxide, and the peroxide would be unstable, whereas dichromate is pretty stable. Okay, so one of the oxygens could be. Bicarbonate, what's the formula for bicarbonate? HCO3 minus. So this is bicarbonate. Bisulfate. HSO4 minus. So we don't have to memorize these. I don't make flashcards for these because I know the pattern. Do you see the pattern?
Yes.
You just take a hydrogen plus and the carbonate and you got HCO3 minus. So the only thing I'd have flashcards for would be the black. Everything else I would know from patterns. And science is all about patterns, right?
So what does the bi mean?
Bi means it's an acid anion. And so there are 2 ways of naming bicarbonate. One is bicarbonate, the other is hydrogen, because you have the hydrogen ion, the acid, carbonate, 2 words. Hydrogen carbonate ion. Bisulfate also goes by the name hydrogen sulfate. How about binitrate? Binitrate is not an acid anion. Binitrate would be HNO3. There's no charge here. If there's no charge, then we call it an acid. When we have acids, I don't memorize the acid names either. You know why? Well, the only reason I asked you to memorize the acid name is because some people don't get these patterns. If you don't get these patterns, then memorize flashcards or do whatever. You know, this one is 8, and if we have an 8, nitrate, then the acid is ic acid. And so we look at the anion. The anion is 8. Oops, anion. If the anion's 8, then this has got to be ic acid. This has got to be, what's the name of this? Nitric acid. If the anion ends in ite, then what's the name of the acid? Aus acid. I don't memorize the ites. You know why? I know the pattern. What's the pattern between an 8 and an ite?
Minus an oxygen.
Minus an oxygen, same charge. So I don't make flashcards for the ites. And so if I want nitrite, it's easy. Nitrite is, well, not nitrous acid, nitrite, the anion. NO2 minus. Sulfite,
SO2.
SO3, just one less oxygen. Chloride,
ClO2 minus.
yeah. And then there's one other ending for ides. The ides are going to form the hydro prefix ic acid suffix. And so, like chloride. Chloride forms hydrochloric acid. The ides I don't memorize either because the ides we get off the periodic table, except for which ones? Ides, these are monatomic from the periodic table. And we know the charge based on the periodic table's position, right? Everybody knows the charges based, like good. So fluoride minus, oxide is,
2 minus.
nitrite is,
3 minus.
carbide is.
4 minus plus.
Yeah. monatomic anions. There are some polyatomics that we have to memorize, unfortunately. What are the polyatomic ides that we have to memorize? Peroxide is one. So what's the formula for peroxide?
O2 2 minus.
O2 2 minus.
Cyanide.
Cyanide, good. That formula is
CN minus.
CN minus.
Hydroxide.
Hydroxide is
OH minus.
OH minus. Peroxide, cyanide, hydroxide. Am I missing any? Can you think of any others? No, that's it. Yeah. I think we're good. So this is similar to Chem 4. Wait. And so potassium dichromate is what we had here. What is the oxidation state of chromium in this compound? So do you guys remember the rules for oxidation state? Let's look at the rules.
Thank you.
So this is table 3.2, assigning oxidation state. So the oxidation state, OS, of an individual atom in a free element uncombined with other elements is 0. So oxidation state of atoms in an element are 0. 2, the sum of the oxidation states of all atoms in neutral species equals 0. In charged species equals the net charge. In their compounds, the group 1 metals have an oxidation state of +1. We have to go in this order. Otherwise, we might screw things up. So first, +1 for the group 1 metals, +2 for the group 2 metals. And so in this case, potassium is group 1. So potassium's oxidation state is +1. And so let me write it up here, +1, and I put parentheses around the oxidation state. In its compounds, the oxidation state of fluorine is -1. So fluorine's special, so -1. 5, in its compounds, hydrogen usually has an oxidation state of +1. So no hydrogen here. In its compounds, oxygen usually has an oxidation state of -2. So oxygen here is -2. If we go in this sequence, we don't always get -2. So for example, if we're looking at hydrogen peroxide, because of this sequence, we end up with oxygen at -1 rather than -2. But we need to go in this sequence, because if we just start here, then we get the wrong oxidation state for oxygen in hydrogen peroxide or potassium peroxide or whatever we're looking at. 7, in binary 2-element compounds with metals, group 17 elements have an oxidation state of -1, group 16 -2, group 15 -3. You know, the way I summarize this, you know, the way I summarize this is like the alkali metals are always what in compounds? Alkali metals are always +1. Alkaline earths always +2. And then we look to the right. You know, you start off with most electronegative. What's the most electronegative element on the periodic table?
Fluorine.
Fluorine, and then work to the left. The next most electronegative would be oxygen. The next most electronegative would be nitrogen. So that's the sequence that we see here. So what we do here is, you know, this is what I do. If I want to try to remember this, I don't usually do it verbatim. I just try to think of some kind of pattern that, you know, that we observe here. And it's usually, okay, group 1, group 2, and then the most electronegative, and then work this way. That's basically what that's saying. Okay, so then we're left with chromium. So what must be the oxidation state of chromium? What is it?
0.
Okay, so let's look at it. What is the oxidation state If somebody asks you, what is an oxidation state, what would you tell them? You know, you probably know the rule, but what is it?
Net charge.
Not the net charge. The net charge is like, for example, dichromate has a net charge of -2. That net charge is actually the sum of all the oxidation states. And so what the oxidation states are, it's the apparent charge on an atom in it. Whatever we're looking at, it could be an ion or it could be a compound. So the apparent charge on potassium is plus. So we have 2 of them, that's plus and plus. We have 2 chromiums, we don't know what the charge is, but we have 7 oxygens. What's the apparent charge on each oxygen? -2, so I'll write it 2 minus. Now, the net charge is going to tell us, the net charge on this is 0. So all these have to add up to 0. And so what's the total negative charge I have here?
-14.
2, 4, 6, 8, 10, 12, 14. Yeah, -14. And then the total positive charge here?
+2.
+2. And then this has got to be plus x. 2 plus x minus 14 is equal to 0. Oh, not x, because I have 2 of them. So I'll call x the charge, and I have 2 of those. So 2 plus 2x minus 14 is equal to 0. Therefore, x is equal to what?
7.
+7.
Sorry, 6.
No, plus 6, yeah. Plus 6. Have you ever heard of chromium 6?
No.
You know, have you ever heard of Erin Brockovich? Erin Brockovich was in the news because she visited Palestine, Ohio. But she's very familiar with environmental disasters like Palestine. And then, you know, in the San Joaquin Valley here in California, there's a lot of chromium 6 in the water, and there are cancer clusters all around there. And so that's, but she's not a scientist. She was like a clerk at a law office, I think. I never saw the movie.
It's good.
Was it? Okay. I should, but everybody is very familiar with the story because of that. But that's typically the case. If there's some accident or some environmental disaster, people try to downplay things. And I don't know. They're saying maybe it's to keep people calm, but maybe it's just to try to, protect themselves, basically, not take responsibility. But anyway, so here we have. This is the notorious chromium 6. Now, plus 6 is a huge positive charge. So typically when you see chromium 6, people use Roman numerals because, how can you get a plus 6? Have you ever seen a plus 6 cation? No, because it's a huge positive charge. Roman numerals are often used to indicate oxidation states like this rather than the actual number here, but it would be plus 6. So what we have here is potassium's plus 1, chromium is plus 6, and oxygen's minus 2. It's the apparent charge on each, not the cumulative charge. The cumulative negative charge is negative 14, but we'd never say the oxidation state on oxygen is negative 14. It would be crazy, an oxygen atom with a negative 14 charge. And the total charge is 0 here. So we have different net charges. We have the net negative charge and we have the net total cumulative charge, which is 0. Oxidation states are important in understanding things. Is oxalate, would you consider oxalate an organic or an inorganic compound?
Organic.
Yeah, I'd consider it an organic compound. Will oxalate combust?
Probably not.
Well, usually when we're thinking about combusting things, we want a fuel and we want an oxidizer. Do you know what oxidizers do? What do oxidizers do? They take electrons. Oxidizers are good at oxidizing things, especially metals. Metals have loosely held electrons, and so metals are usually easy to oxidize except for some of them. Some metals are very difficult to oxidize, and we call those noble metals. Which metals are especially difficult to oxidize?
Palladium.
Platinum, palladium,
Nickel.
nickel,
Gold.
gold,
Silver.
silver. Silver is a lot easier to oxidize than does. So silver is okay, but much more reactive. What about copper? Copper,
Oxidizes extremely easily.
not extremely, but still it's, so I don't know where the cutoff for Nobel. These are the coinage metals. And so you don't want your coins to corrode.
What about zinc?
Zinc is not. Zinc is very easy to oxidize, surprisingly.
I just wanted to.
And this is the problem. You know, the little kids eat the pennies, and the copper coating is not. They end up with zinc poisoning. Yeah.
And that's no good.
No, because pennies are mostly made of zinc. Actually. But so we need a fuel. So metals. Do you know metals can act as fuels? You know, I didn't know this. Like when I was in the Boy Scouts, you know, or maybe it was even the Cub Scouts. We went camping, and you know what we used to start the fire?
A flint and steel. A flint and steel.
What?
A flint and steel.
A flint and steel, yeah. Well, flint and steel to make the spark, right?
Yes.
But what did we use as a fire starter? Usually you gather twigs.
Oh,
And
I
stuff.
use a, I think it's called a therium rod.
Okay. Well, you know, as just to start your little baby fire, to let it grow into a big fire. We use steel wool, and initially I was thinking steel wool. What? Steel doesn't burn. That's what I was thinking originally. I thought steel. There's no. What are you using steel wool for? Bringing steel wool, but you know, steel wool was an excellent fire starter. It burns really nicely, yeah. And so we use steel wool.
What's interesting about steel wool I learned from like a YouTube short was instead of losing mass, it gains mass from burning.
Oh yeah, isn't that weird? Yeah.
Because it takes in the oxygen.
Right, it's taking in the
basically.
oxygen. That's it. Like you know those hand warmer packs. You know, I was looking at that. That looks like finely divided iron. So it's just slowly combusting and generating heat there, creating rust. Yeah. Since most of the iron on Earth is rust, you can make it though. You can make just pure iron. But anyway, these are actually good fuels. And when you buy a metal, you know, oftentimes it's written flammable on the container. You have to watch out because metal fires can be quite dangerous. But there are things that burn easily. A lot of organics burn easily. So, for example, like oxalate, would you expect that to burn? And how good of a fuel is it? If we compare to acetate, is acetate combustible, like acetic acid? Could you burn that?
I wouldn't think so.
You don't think so? It's not very explosive. But like your body burns things too. Your body is going to burn food, which it uses as fuel, and it's the same process in certain respects. Not the exact same mechanism, but overall the same process because you eat. What do you eat? You eat carbohydrates. We'll talk a little bit about that. You eat proteins. You eat fats. And essentially you burn those. And when you burn those, you exhale the products of combustion. What are the products?
CO2.
CO2 and H2O. And then there's also energy, but we use energy. But anyway, do you know, are there people, can you get calories from eating acetic acid?
No.
Is it 0 calories? Because if it's 0 calories, then if we consume acetic acid, vinegar, then that's pretty much calorie free. You know, so like those vinegar and salt, you know, French fries, you'll get a lot of calories from the potatoes and the oil, but will the vinegar add to calories? Like for example, sodium chloride. If you sprinkle sodium chloride, is your body going to burn the sodium chloride?
No.
Produce energy?
No.
Likely not.
No. And so sodium chloride I expect 0 calories. But if you were to eat acetic acid or sodium acetate, on the other hand, not sodium chloride, but sodium acetate, would you get calories from that? And so this is what we're looking at. We're going to start using oxidation states. What do they say about oxidation states in this chapter?
Oh, it's
Oxidate, a useful tool in describing chemical compounds. And this is extremely useful. So most basic concepts in chemistry deal with measurable properties and phenomena. In a few instances, though, a concept has been devised more for convenience than because of any fundamental significance. This is the case of oxidation states. Yeah, this is for convenience. This is a different way of counting electrons. We have like 4 different ways that we count electrons in compounds. Even though you're never going to see a chromium plus 6, you know, this is very useful because then we can compare that to other things, you know, like a chromium plus 4 or chromium plus 5, you know, it's going to react differently than a chromium plus 6. And so this is going to give us a lot of useful insight. Although the assumption that we make, when we come up with these numbers like this, we're assuming all the bonds are ionic, 100%, unless it's a homo atomic bond, that is the bonds between 2 of the same atoms, versus a hetero bond. But anyway, the thing here is this. It's going to be plus 6, but even though we don't see that in reality, we still use that. And so what we need to do is we need to look at chromium, and then we look at what kind of range of charge or oxidation states do we expect. And then from that, we can get some idea of what to do with these numbers. And so for chromium, can you tell me what the oxidation states are?
Is it plus 2, plus 3?
Yeah, for most of the transition elements, we expect plus 2, plus 3. For most of these. Except some of these we expect plus 1, plus 2. Which ones do we expect plus 1, plus 2?
Titanium.
Not titanium.
When did that?
Was it manganese and rubium?
I was gonna say
Not
when
just
did-
those 2.
Then you already had plus 3 oxidation states. So
My guess is manganese.
Do you guys know the different periodic tables with the Roman numerals versus the...
No. I didn't know you made different periods.
the different numbering systems?
How many different numbering systems are there?
A lot.
3.
3.
Actually more than 3, but...
whoa.
Is that between numbers?
I like the Roman numeral. My preference is this Roman numeral system versus this. This is the new one, and everybody's using this one, 1 through 18. And our book's using that too. The reason I like the Roman numeral system is, do you know what the Roman numeral stands for?
The oxidation state.
The maximum oxidation state. And so, so for example, chromium, do you know what the maximum oxidation state is on chromium?
6.
Plus 6. And so this is the max, plus 6. That's going to dictate, you know what that means? It means we can't go to plus 7. Oh, we could, but it would be very weird and very reactive. And so plus 6 is maxed out for chromium. What about manganese? What's the max?
Oh, 7.
Plus 7.
7 oxidation states.
Yeah, and titanium? Plus 4. Now for the transition elements can have variable charge. So for example, chromium can have plus 1, plus 2, plus 3, plus 4, plus 5, plus 6.
and then stop. Manganese can have, well, it can have 0. And so in chromium metal, it'd be 0. Manganese could have 0 in manganese metal, and then +1, +2, +3, +4, +5, +6, +7. Yeah. And so we'd have all those. Those are the variable charge ones. Now we have fixed charge. And so potassium is fixed charged at +1. Calcium is
2,
Scandium is 3. Titanium is
4.
Now, losing 4 electrons is difficult. Have you seen very many titanium +4 ions floating around in solution? No. And so titanium is the beginning of the variable charge because that's getting high. +3 is okay, like iron +3, chromium +3, etc. Those are fine. But for titanium, it's going to be +1, +2, +3, +4. Now, there's something called the most common charges. The most common charges of these guys here are +2 and +3. And so manganese +2, +3. You know, to get to +7, that's going to be unstable. And that's going to dictate how we treat things. You know, so for example, like dichromate, I worry about this stuff. I worry about this stuff because automatically I see chromiums in +6, meaning it's not so stable. It's kind of unstable. Does that make sense? Yeah. But if chromium was in the +2 state, then no big deal. Or chromium in the +3, it's a lot less hazardous to your health than chromium in the +6. So this is where, like Aaron Brockovich was, you know, it's the chromium in the +6. Oddly enough, what about chromate? What's the oxidation state of chromium and chromate? It's also +6. So either one of these we call chromium 6. And both of these cause trouble. They use chromium 6 in lots of different things like tanning leather and concrete and other stuff. There's a neighbor was pouring a new concrete patio and just made this huge dust cloud, concrete and all kinds of stuff. And this huge dust cloud came into the backyard and coated everything with this. And I'm thinking, now I got chromium 6 everywhere. Hopefully it rains soon or something. But then it gets into the groundwater and what else.
It's going to rain Thursday. It's going to rain
Well,
tomorrow.
this happened years ago. I was thinking, well, anyway, can't do much about that.
Yeah, the forecast for tomorrow, 50% chance of rain.
Yeah, well, rain is good. Rain. All right, so these I like, but take a look at what happened with copper. And then this is a +8, +8, +8. Iron, cobalt, nickel. Iron, cobalt, nickel are kind of interesting. These are the magnetic ones. And then copper went down to 1. And so copper is an honorary group 1 element because copper can form +1, but also it forms +2
as well.
However, silver is a good one because silver only forms +1. So this is a good honorary alkali metal, but it's not. It's a gold. You know what the charges on gold are?
+1,
+1.
+1 and +3. So it gets a little bit more complicated, but these are kind of +1. And then these are
+2,
+2. So zinc is always
+2.
cadmium.
+2.
Yeah, so zinc, cadmium, and silver are fixed charge. So this is the fixed charge island in a variable charge C. Mercury is
+1,
+1, +2.
+2.
These ones like to go in the variable charge. These ones like to go +3, +5. Or no, +3, sorry. +3. +3, sometimes thallium +1. Tin likes to go what? +4. Lead?
+4.
But getting +4, yeah, these are variable. 2 and 4.
2 and 4.
Yeah, 2 and 4. These are 3 and 5. But it's all right. So what we know is the common ones are 2, 3, 1, 2, and 2, 4. Those are the most important ones. Do you guys know those? Pretty much? Yeah, good. Okay, so let's get back to the question. What makes a good fuel? something that's rich in electrons. Fuels are what we call electron rich. Oxidizers are electron poor. So chromium metal by itself would be a fuel. It has electrons. But would you expect dichromate to burn? So for example, in Palestine, they said, okay, we're going to incinerate everything. You incinerate chromium-6, is it going to burn? No, it's already been an exhausted fuel. It's just going to stay chromium-6 unless you have a reducer. Sometimes what they do in incinerators are really complex. And incinerators can make things much more environmentally friendly. But in this case, no, we're not going to be able to really incinerate this because it's been what we call completely oxidized. And so what we want to do is we want something that we can oxidize, that is take electrons from. And so if we look at carbon, what is the range of oxidation states for carbon?
Is it like +4, -4?
Yeah, +4, -4. Do you know where I get those from? Or where did you get it from, Lily?
Well, because you could go forwards 4 or backwards.
Yeah, so if we go forwards 4, we end up with 10 electrons, which would be isoelectronic with neon. And that would be good because noble gases, the filled shell. Or if we lose 4, we would be isoelectronic with helium. And so we could lose 4. If we lose 4, then on one end, it's +4. If we gain 4, on the opposite end, it's going to be -4. And so this one is considered electron poor, carbon. This one over here is considered an electron-rich carbon. And so we have examples of this. Let's give an example of an electron-poor carbon. Let's say, I have too much CO2 in the air. Can I go ahead and incinerate the air, get rid of the CO2? Will incineration work to get rid of the CO2 in air?
It will not.
It will not. Why? It will not, because if you try to incinerate it, you're trying to burn it, and to burn it, the oxidizer, oxygen, needs to take electrons. Are there any more electrons on carbon for oxygen to take? No, therefore oxygen would have to take them from oxygen. Do you think oxygen will take them from oxygen? No. Whereas, how do I know this is +4? Well, the way we do it is the more electronegative oxygen is going to get its usual charge, which is -2. And if oxygen is -2, we have 2 of them. So 2 times -2 is -4. Therefore, carbon must be +4. Give me an example of this is something, when they blew up whoever blew up the pipeline released a huge amount of this gas into the air. What was the gas they released? Methane. Methane, do you know in terms of greenhouse, methane is way worse than CO2 in terms of greenhouse. So that was a greenhouse disaster there with the blowing up of that pipeline, because it's better to burn it and create CO2 than to leave. In fact, they're talking about getting rid of not getting rid of cows. Well, there was talk about getting rid of cows.
All the cows.
Yeah. They're talking because, when they digest things, they burp a lot of methane. And so they're talking about either, reducing the population of cows or getting rid of cows altogether, which I don't think is.
It's most likely.
There's too many dairy cows.
Yeah. Or, they're chemists. They're chemists that are trying to look at the chemistry of the cow's digestive tract. And so one of the things they're looking at is feeding them seaweed. Certain types of seaweed have shown to reduce the amount of methane that's emitted. So maybe the cows still have a chance. But anyway, the reason why methane is such such a bad greenhouse gas is when you get to these more complicated structures, you know, CO2, do you remember the Lewis structure for CO2?
Yes.
Linear, right?
Yeah.
Whereas methane is tetrahedral.
Tetrahedral.
And so this can vibrate in a lot more different ways, and then it could absorb more of the infrared or whatever, cause global warming. Anyway, this one, which one do we do first, carbon or hydrogen?
Hydrogen.
Hydrogen goes at +1. And then carbon, that means carbon must be -4. So this is the prototypical, this is the excellent fuel because the carbon is so rich in electrons. And over here, this won't burn. However, you know what would burn is, let's say you're worried about carbon monoxide poisoning. Will incineration work for getting rid of carbon monoxide? Yes. Incineration will work for getting rid of carbon monoxide because each carbon can lose how many more? Because the carbon here is, well, oxygen's -2, we have one of them. That means carbon is +2. So carbon has 2 more electrons it can lose. And so incineration will work for carbon monoxide. It will not work for carbon dioxide. Because carbon dioxide is what we call maxed out. It's no longer, just like chromium-6, it's maxed out. And that's it. Okay, so let's look at acetate next, like acetic acid. You know, will you get calories from vinegar? That is, can you burn vinegar in your body? So let's see what the oxidation states are. Hydrogen, carbon, oxygen, which one goes first? Hydrogen. So that's
Hydrogen, of course.
+1. This is +1. Then what?
Oxygen.
Oxygen at -2. And that means carbon is what? Carbon's variable charge. You know, carbon can be anywhere from +4 to -4. And so we got to figure out what it is in this particular instance.
Shouldn't the H be a 3?
Because it has H3.
Yes. Good. I don't know why I was thinking 2. You know how long it took me to memorize acetate? So long. 2, 3, 2. So, you know, I had different things. 2, 3, 2 minus, 2, 3, 2 minus, 2, 3, 2 minus. And then writing it down. Flashcards. I did flashcards initially. Mm-hmm.
With what's written up there, do you have a hydrogen in front of the acetate?
Yeah.
Acetic acid.
Yeah.
This is for acetic acid.
Acetic
So,
acid.
you know, will eating sodium acetate give you calories? Eating sodium chloride is not going to do anything except, you know, make the food taste salty. It's not going to give you calories because your body's not going to metabolize it. Will eating sodium acetate or acetic acid give you calories? Well, what is carbon's oxidation state?
No,
So I go +1 plus 3 is +4. +4 minus 2 times 2 is -4. +4 minus 4 is 0. All these have to add up to, therefore carbon must be 0. So if carbon is 0, then it's right in the middle of this, right? And so carbon can lose, each carbon can lose 4 electrons. We have 2 of those, and that gives us 8 electrons. And so acetic acid will give you calories. It's so vinegar, when you eat the vinegar, it's not calorie free.
Could you have one carbon each with opposite charge for each other?
Yeah, that's a good point. This is what we call the average. They aren't going to be opposite in charge. This is the average. When we get to Lewis structures, I do these totally different. And so these rules I don't, you know, they're useful to know, but when we do the Lewis structure, we get a much better picture of what's going on. What we assume in oxidation state is the bond is 100% ionic. In 100% ionic bonds, winner takes all. Carbon versus hydrogen, the winner is the more electronegative one. So which one's more electronegative? Carbon. Carbon takes all from hydrogen. Carbon versus carbon, it's a tie. This is what I meant by heteroatomic versus homoatomic bonds. It's a tie. And then we count the electrons. Carbon ends up with 1, 2, 3, 4, 5, 6, 7. Carbon ends up with 7. How many valence electrons does carbon normally have? 4.
4.
And so it has 3 extra electrons. 3 extra electrons means a -3. So this left carbon is -3 oxidation state. That's pretty rich, right? That's on the electron-rich side. The right carbon, okay, carbon versus carbon, tie. Carbon versus oxygen, who wins? Oxygen.
Oxygen, of course.
Carbon versus oxygen? Oxygen.
Oxygen.
This carbon only ends up with 1 electron. It's supposed to have 4. It lost 3. And so this one comes out to +3. So in this case, that you're right. But in other cases, they're different. You know, could be different. And so here, that's a -3 and a +3. +3 is almost maxed out. And so this stuff won't burn as well. This stuff will burn great. Does that make sense for this? And so acetic acid has calories. Sodium acetate has calories. Potassium acetate has calories. You could eat this stuff and survive. And so if you ran out of food and you have a bottle of sodium acetate on the shelf, you might consider eating sodium acetate because you might survive. Whereas if you have a bottle of sodium chloride, you might not survive.
I'm pretty sure there's going to be a lot of health problems if you survive off just vinegar.
Yeah, probably. But vinegar, if you take biochemistry, you'll learn about vinegar, or acetate, and acetic acid, and those kinds of stuff, because those occur in the metabolic cycles in your body. Don't eat oxalate, because oxalate is poisonous. I think because of the stones or something, kidney stones or whatever. But would you get calories from eating oxalate? Let's say you survive. Could you burn oxalate?
No.
Let's say oxalate's a poison. There's a huge disaster, spill of oxalate everywhere, oxalic acid. Could you go ahead and try to incinerate it? If you try to incinerate it, the oxalic acid might make what? CO2, and maybe that's better. CO2 might be better than oxalic acid everywhere. Although, you guys did pretty good with the balances. The afternoon class left huge mess of oxalic acid everywhere. I spent like 30 minutes cleaning up all the oxalic acid everywhere, and I was thinking, oh, I'm going to poison myself. Oxalic acid.
No,
But-
Mr. Shabbat, don't poison yourself, please.
Anyway, could oxalic acid be incinerated to make CO2?
Yes.
Okay, and it could be potassium oxalate or sodium oxalate or whatever. Could that stuff be incinerated? And the answer is yes, it can. So if we look at oxalate and oxalic acid, they're going to have the same oxidation states. And so we just handle it a little differently. So oxygen is
-2.
-2. Carbon is
+3.
+3. It won't burn very well because it's almost maxed out. But you should be able to burn this to CO2. Does that make sense? And the same thing here. This is -2 +1, and then this is going to be +3. And so oxidation states are very useful in what we call redox reactions. And so let's take a look at finishing the question here. What's that?
Was it?
88.
Oh, 88.
88, all right.
Say
Yeah,
86.
I think it was the previous page.
There it is. What is the name of the compound? So we got the name.
And we got the oxidation state formula as well.
Yeah. Yeah, good. So we're finished with that particular problem. Now we're going to look at the other type, or the other method, which is combustion analysis. So we just talked about some memorization here. And so combustion analysis, we need, first off, we need something we can burn. Hydrocarbons are great. Hydrocarbon. Compounds of hydrogen and carbon. And then we have HCO or CHO. You know, CHO compound. You know, these are some of the acids, organic acids. These are like alcohols. We have others called ethers, etc. Then we have these ones. We have CHN. We have CHS, and then we have combinations, etc. When nitrogen burns, do you know what we can burn it to? What's the max on nitrogen? So if we look at nitrogen, what's the range of oxidation states for nitrogen? Plus 5 to, not minus 5, to minus 3. Usually nitrogen only goes to plus 4. And NO2 plus 4. To get it to plus 5 is a bit more difficult. So when you burn nitrogen, it usually maxes out at plus 4. Sometimes it just goes to plus 2, NO. You don't want to burn nitrogen containing things because NO and NO2 are toxic. You know, NO2 is the brown gas you see in smog or diesels. Have you ever followed a diesel truck and you see the brown gas? And the smell, it's like a suffocating smell. The suffocating smell oxides of nitrogen, NO2. This is why when I follow diesel, I put on recirc. I don't want to be breathing oxides of nitrogen like this. Sulfur, what are the range of oxidation states for sulfur? Sulfur varies from plus 6 to minus 2. And so this one, sulfur trioxide, is the ultimate, and that would be plus 6. So when we burn sulfur, it depends on how completely you burn it. You know, so we get sulfur dioxide, incomplete, sulfur trioxide, complete. Nitrogen dioxide is not quite complete, but you know that's kind of where it stops, because to get to plus 5, you'd have to have what, N2O10. And then you'd get to plus 5. I think. Is that right? Or NO5? No, that's wrong. What is this? Minus 2, minus 20. No, that's plus 10. 5. N2O5. This would be maxed out, right? N2O5. But all these are quite poisonous here. So when we burn things that contain nitrogen or sulfur, you should do it in the hood. You know, not in the open lab. Methane is one of the cleanest burning fuels, you know, as far as generating CO2. Unfortunately, CO2 has problems.
What kind of problems do you encounter with burning things into CO2?
One is, we're okay with low levels of CO2, but when the CO2 concentration gets high in a room, you start to feel sleepy. And then if it continues to get higher and higher, it becomes lethal.
Yeah.
All right.
And so if you have too much CO2 in air, this is why on the space shuttle, they have too much CO2, and so what they have are CO2 scrubbers to remove the CO2 in the air on the space shuttle. Otherwise, you could turn toxic, poisonous. Right?
I'm curious how the CO2 scrubber works.
Well, CO2 scrubber is easy. CO2 scrubbers, they use lithium hydroxide as a CO2 scrubber on the space shuttle. It's a simple chemical reaction.
Cool.
So what are the hydrocarbons? Well, let's take a look at naming some of these here. Do you know naming organic compounds? Let's talk about names. Organic compounds abound in nature. The foods we eat are made up almost exclusively of organic compounds, including not only energy-producing fats and carbohydrates and muscle-building proteins, but also trace compounds that impact color, odor, flavor to these foods. Almost all fuels, whether used to power automobiles, trains, trucks, airplanes, are mixtures of organic compounds of a type called hydrocarbons. Most of the drugs produced by pharmaceutical companies are complex organic compounds, as are common plastics. Plastics are a big environmental problem right now, fortunately. The multiplicity of organic compounds is so vast that organic chemistry exists as distinct and field in chemistry. Yeah, the organic compounds, there's so many of them, they had to separate off as a different branch of chemistry, basically. And so let's look at, they characterize them based on composition and structure. So the first ones are the hydrocarbons, but this is for any organic. And so what you need to do is you need to remember the prefix. This is what we call the parent. The parent depends on how many carbon atoms you have. So if you have one carbon atom, we call that meth. And so methane. If you have two carbon atoms in the chain, then we call it F. 3 carbons, this is the longest chain because there could be branches. Carbon's very interesting in that way. You can branch off in different directions. This would be called prop.
Oh, probe.
Yeah. Like propane.
I was thinking of prop, like propeller.
Yeah, but they don't call it. Organic chemists don't call it propane. I've never heard it. It's called.
I would actually say it's propeller, not propeller.
Oh, okay. There you go. If you have 4 carbons, now the carbons don't have to go in a straight line. The carbons can zigzag like this. That's because when we draw Lewis structures, we don't care about the structure. We just draw, right? And so this has 4 carbons in the chain. We're going to call it bute. And so the parent chain is 4. And then 5 carbons,
Pent.
any way you want. Pent. 6,
Hex.
7,
Sept. Oh, hept.
hept. H-E-P-T, hept. 8,
Oct.
oct. 9,
Non.
oh, people call it known, no name, for example, or non, that's all right. 10,
Deck.
deck. So, the ending we have for hydrocarbons, there are 3 endings that we have for hydrocarbons. We have an ane ending, all single bonds. And then the rest is hydrogen. Then we have the ene ending. The ene ending is a double bond. Double bond looks like this. And so this would be an ene. An ine ending with Y and E has a triple bond. And so this would be an ine here in the structure. Ine or ene, the pronunciation varies. So we can give you an example. Ethane looks like this. This burns very nicely, ethane. Ethene also burns very nicely. Ethene looks like this. That's ethene. And ethine also burns very nicely. All three of these burn nicely. Ethine. Ethine goes by a different name. There's a common name for ethine. The common name for ethine is called acetylene. And ethine's very popular with welders. They have acetylene oxygen torches that they use for welding metals. Oxyacetylene torches. And then we have propane, butane, pentane. We just fill in the rest with hydrogens. And unfortunately, we're out of time here. But you'll want to start looking at.
Question. If you can go past the stem into a number of 11 compounds with carbon atoms, would you add meth in front of deck like you would in geometry?
They have a different name. Like,
Because in geometry, once you get to a 10-sided figure, after you go past that, they either call it 11-sided or deck. Then you get to dodeck, trideck.
oh yeah, well, dodeck is used. Dodeck. Yeah, actually, yeah, maybe it is. Undeck, dideck.
I was about to ask, is it called a my deck for ME? Or would it be a meth deck?
I don't know.
Honestly, meth decks on sale.
Yeah, that doesn't sound fun.
I used to work with a dodeck.
I remember I
Bye, Mr. Chabot.
Bye.
looked up the, geometric sides, right? Up